This unit of study deals with soil water. Water is a precious resource that is basic to all forms of life. Agriculture depends on usable fresh water, which is a very small fraction of our total water supply on Earth. Globally, 97% of the total water is not usable for direct consumption by plants, animals, and humans. Plants absorb most of the water that is essential for their growth and production of dry matter through their roots. Soil water is a key resource to crop production, and in many situations may be the major yield determining factor. The amount of water necessary to operate a family farm with crops and livestock in the central part of the U.S. is phenomenal. Even small crop and livestock farms use hundreds of thousands of liters of water per day. The evaporation of water off of the soil surface and the transpiration off of plant leaves together is called evapotranspiration. This is by far the major use of water on a farm. This evapotranspired water comes primarily from the soil water supply, either through rainfall or irrigation. An understanding of the relationship between crop growth and soil water is necessary to ensure efficient and prudent use of this precious resource. The next topic for study is the section on water in the soil. You should now stop the VCR and study this section in your text. Then return to the VCR for further tutoring. Soil structure and texture are important factors affecting moisture availability to crop plants. Soil porosity, pore size, internal drainage, water holding capacity, and water available for plants are related to soil texture. In general, coarse textured soils have excellent internal drainage, poor water holding capacity, and poor water availability for plants. In contrast, fine textured soils have poor internal drainage, excellent water holding capacity, and good water availability for plants. This is partially due to the surface area of the three soil separates: sand, silt, and clay. Clay particles have much more total surface area to hold moisture than larger sand or silt particles. This is due to clay's smaller particle size, which allows for a greater number of particles in a given soil volume. Consequently, soils with higher clay content hold more moisture than sandier soils. Water is held to soil particles by forces of adhesion and cohesion. Water of adhesion is held by the attraction of the soil particle and is usually a very thin layer. Water of cohesion is held by the attraction of other water molecules. It's important to realize that as the thickness of the film of water around the soil particle increases, the forces holding the water diminish, thus making the water more available to plants. The next section for study is soil water concepts and terminology. You should now stop the VCR and study this section in your text. Then return to the VCR for further tutoring. Water flows through the soil due to the forces of gravity and capillary action until the water surrounding the soil particles is held with a suction of about 1/3 bar. A bar is a unit commonly used to express suction force and is approximately equal to the normal atmospheric pressure of 14.7 pounds per square inch, or 1 kilogram per square centimeter. At 1/3 bar, the soil is at field capacity. Plants can readily absorb water through the roots and use it for maintenance and growth when the soil is near field capacity. As water is used or evaporated from the soil, it becomes less available to the plant until it reaches the permanent wilting point of about 15 bars. At the permanent wilting point, the plant wilts and growth ceases. Capillary water, especially that between field capacity and the wilting point, is the only important source of water for crop plants. If enough moisture is received, the macropores in the soil are filled with water. The excess water that is moved by gravitational force is termed gravitational water. Excessive gravitational water may injure plants. If drainage is too slow, the soil may be lacking in oxygen, resulting in poor root growth and function, and often encouraging the growth of some species of disease organisms. Hygroscopic water is a thin layer of water remaining on the soil after it's dried. At 31 bars, it's held far too tightly for crop roots to utilize. The availability of soil moisture to the plant, the movement of soil moisture to plant roots, and the rate of water movement in the soil and in the plant all depend on soil, plant, and atmospheric factors. These factors include soil texture and the suction forces between soil particles and water, as previously discussed. Soils with good structure, organic matter, and earthworm activity increase soil water holding capacity and improve internal drainage and aeration. These factors improve root growth, which in turn helps plants absorb soil water and avoid wilting stress. Plant factors such as leaf and stomatal anatomy regulate water loss from the plant and water uptake rates by roots. The depth and density of root systems also influence the ability of crops to extract soil water. Humidity, air and soil temperature, and wind velocity are important atmospheric factors that influence rate of water loss and uptake. In general, higher air and soil temperatures, greater wind speeds, and lower humidity increase evapotranspiration rates. The types of soil water, and most importantly, the amount of plant available water, varies greatly among soils of different texture. Fine textured soil, such as clay loam, holds more moisture of all classifications, hygroscopic, gravitational, and plant available water, than does a coarse textured soil, such as a sandy loam. It's important to realize that the total amount of water held at field capacity does not necessarily mean the greatest amount of plant available water. Clay soils will hold as much or more moisture at field capacity than other soil types. But a large proportion of the moisture is held at a suction strong enough to make it unavailable to plants. Silt loam and clay loam soils have more plant available moisture. Crops are drought prone on sandy soils because sandy soils hold little water. Although sandy soils hold small amounts of unavailable water, little is held at field capacity. Thus, the amount of plant available water is small and quickly used up by plants in hot, dry growing conditions. Sandy soils at field capacity hold less than 8 centimeters of plant available moisture per meter of soil. Up to 21 centimeters per meter may be available in clay or clay loam soils. The next section for study is soil moisture and crop management. You should now stop the VCR and study this section in your text. Then return to the VCR for further tutoring. Cropping systems and tillage systems influence the amount of runoff and therefore the amount of infiltration. Crop management practices also influence the rate of water loss from soil by influencing evapotranspiration rates. Crops vary in the amount of water uptake and rate of water loss from transpiration. A summer annual, such as corn, will generally remove less soil moisture than a perennial meadow or hay crop. This is because the meadow or hay crop has a longer growth period than an annual crop, such as corn. Some short-season crops, like the small grains, escape drought by maturing before hot, dry weather. In this case, the crop would be called a drought escape crop. Other crops, like alfalfa and sunflowers, tolerate hot, dry conditions because of relatively deep rooting characteristics. Grain sorghum has waxy coatings on plant surfaces that reduce plant water loss, enabling it to live under drier conditions than other crops. In these examples, the crops would be called drought-tolerant crops. Plant population can also affect evapotranspiration rates and thus rate of soil water loss. In general, evapotranspiration rates are higher in fields with more plants per unit area than fields with lower plant populations. But the water use efficiency may be higher too. Water use efficiency is the amount of dry matter produced per unit of water used. Frequently, water use efficiency is greater using narrower row spacings and higher plant populations. This is due in part to the higher grain yields often achieved with narrower rows and higher populations. Doubling the number of plants per unit area does not necessarily double the evapotranspiration rate. Therefore, producing higher grain yield using narrower row spacings and higher plant populations without using more water results in a greater water use efficiency. This same principle has held true in soybean production. Soybeans growing in narrow rows spaced from 18 to 38 centimeters apart have higher total water use per acre during the growing season. But the yields of grain per acre have usually been large enough to result in a greater water use efficiency. There are many other management practices that can be used to help conserve water for crop growth. For example, reducing the amount of tillage and leaving more crop residue on the soil surface will help reduce evaporative loss from the soil surface. Another example of water conservation is controlling weedy growth to prevent unnecessary transpirational loss from soils. The next section for study is irrigation. You should now stop the VCR and study this section in your text. Then return to the VCR for further tutoring. Irrigation is the artificial application of water to soil in an effort to enhance crop growth. In many areas of the world, irrigation is used to provide the amount and distribution of water needed for crop production. Irrigation may also be used in more humid regions where natural rainfall may not come at needed times, or where the soils are too sandy and do not hold enough water for adequate crop growth. Of the total irrigated land in the world, most is found in the arid or semi-arid regions. In the United States, most of the irrigated land lies west of the Mississippi River. There are many advantages of irrigation. Food production in arid and semi-arid regions has greatly increased due to improved crop yields on land that otherwise would be too dry to grow crops. Timing, rate, and amount of water application can be controlled, thus helping control runoff and infiltration. There are also disadvantages and concerns of irrigation. Irrigation and irrigation equipment are expensive and add to production costs. One of the biggest concerns is the effect of irrigation on our fresh water supplies. Almost 75% of the global freshwater supplies are used for irrigation. Excessive withdrawal for irrigation can severely lower freshwater levels in streams, lakes, and underground aquifers, affecting wildlife, recreation, water navigation, public and industrial use, and groundwater contamination. The importance of maintaining adequate freshwater supplies through sound management and water conservation practices cannot be overemphasized. Irrigation is frequently divided into four major types: surface, subsurface, sprinkler, and trickle or drip irrigation. Surface irrigation is usually conducted by flood or furrow methods. Water is brought to the field by open ditches, pipes, or other means. If flood irrigation is used, the ground is usually leveled and slightly sloped, and water is applied so that the entire field surface is flooded. If furrow irrigation is used, the ground is ridged and water is applied to the field in the furrows made by the ridging operation. In both methods, water moves through the field by gravity, which requires nearly level land and leveling operations to provide the proper slope for water movement. Subsurface irrigation can be achieved by raising the underground water table to a depth that can be reached by the roots, or by pumping water through pipes placed underneath the field surface. Sprinkler irrigation is a commonly used method, especially on sloping land. Water is frequently obtained from wells drilled into the aquifer or pumped from rivers or water holding devices. Water is applied through stationary or traveling sprinkler units under pressure to force water through small sprinkler orifices. Center pivot irrigation is popular in the Great Plains region. The circular irrigated area under one center pivot may cover up to 49 hectares or more. Trickle or drip irrigation is increasing in use, especially in areas where water supply is limited and minimum water loss is desired. Water is piped to the field and delivered to plants at slow but constant rates. Trickle irrigation has resulted in good yields at only a fraction of the water used in other systems. The next section for study is salt accumulation. You should now stop the VCR and study this section in your text. Then return to the VCR for further tutoring. Salt accumulation is a serious problem in arid areas and where irrigation is practiced. Soil water containing soluble salts is brought to the soil surface through evaporation. As water evaporates from the soil surface, soluble salts are left behind, accumulating to toxic levels that prevent or impair crop growth. The remedies for salt accumulation or saline soil conditions are limited. Some crops can be selected that are more tolerant to saline soil conditions than others. Flood irrigation has been used to leach the salts to deeper soil depths out of the primary root zone. But this is temporary because salt accumulation steadily continues under the high evaporation rates occurring in these climatic conditions. In severe cases, cropland has been abandoned because of chronic salt toxicity. The next section for study is soil drainage. You should now stop the VCR and study this section in your text. Then return to the VCR for further tutoring. Excessive soil moisture can be just as detrimental to crop plants as insufficient soil moisture. Excessive soil moisture can lower or prevent the proper aeration of soils needed for adequate root growth and function. To remove excess water, external and internal soil drainage are used. Surface drainage may be accomplished by diverting excessive water off the field using terraces or shallow surface ditches. Internal drainage may be accomplished by tiling the field with porous subsurface tile. Tiling soil has been a very effective way to make productive land out of soil that normally is too wet for crop growth. Although soil drainage has been successful in improving land for crop production, widespread use has been extremely detrimental to wetland habitats. Naturally formed wetlands also serve as environmental filters for soil water contaminants. The soil helps filter out sediments, pollutants, and chemical contaminants that would otherwise be diverted into ditches, streams, and rivers, which can be detrimental to other wildlife dependent upon this freshwater supply. Thus, conservation of our wetlands has both practical and aesthetic value that should be an integral part of a sound water management program for agricultural use. Water is truly the key to plant, animal, and human life. Agriculture throughout the centuries has flourished or withered based on the supply and quality of fresh water. Managing this precious resource will determine how effective we are in developing a sustainable agriculture, now and in the future. This is the end of the chapter on soil water. You should now be ready to try the self-evaluation test at the end of the chapter in your text.